You clicked because you remembered the textbook answer. Salt melts ice. It lowers the freezing point. That's true. That's also 140 years old. It's not the whole truth. It's the opening of a case that physics is still trying to close. Picture a highway at night, a snowstorm, a truck spraying white crystals across the asphalt. Salt. Roman soldiers spread it on frozen roads 2,000 years ago. Today, the United States alone uses roughly 6 million tons per year. Every driver trusts it. Every city engineer. Every road crew. It works. But ask a physicist why it works. Actually, why at the level of individual atoms. And watch what happens. But that simple answer unravels into quantum effects and the mystery of why hot water freezes faster. Salt dissolves into sodium and chloride ions. Those ions disrupt water's ability to form an ordered crystal lattice. Fewer water molecules can lock into ice. The freezing point drops. That's the colligative property, formalized by Van Hoff in the 1880s. Thermodynamic entropy, clean, solved. Except that explanation is macroscopic. It says nothing about what salt actually does to individual water molecules. And it fails to predict what a 2022 simulation would reveal. In the Journal of Chemical Physics, a team used the Madrid 2019 water model to simulate saltwater freezing, revealing that classical simulations failed to match experimental results. Classical molecular dynamics, the kind that treats atoms like tiny billiard balls, failed. The simulated freezing point depression didn't match experiment, not even close. To make the simulation match reality, the researchers had to include nuclear quantum effects. That's not nuclear as in fission. It's the quantum waviness of atomic nuclei, zero-point motion, delocalization, tunneling. The nuclei themselves had to be treated as quantum objects, not fixed points. Without them, the simulation lied. The textbook answer is wrong. It's incomplete. A salt crystal on a road is a quantum system in disguise. And there's more. The ion doesn't just disrupt the water molecules it touches, it reaches further. A PNAS paper on hydrogen bond symmetrization in ice showed that ions alter hydrogen bonding beyond the first hydration shell. 2, 3 layers deep. Classical electrostatic models can't reproduce that. The disruption is long-range, non-classical. That's not what the old textbooks predict. The ion sends ripples through the hydrogen network. The picture of salt as a simple lattice breaker is a sketch. The evidence demands a quantum correction. So salt works, but the why is more profound than anyone expected. Now consider a second anomaly. A different file in the same cold case, the Mpemba effect. In 1963, a Tanzanian schoolboy named Erasto Mpemba was making ice cream. He noticed the hot mixture froze faster than the cold mixture. His physics teacher dismissed him. Dismissed, the boy persisted. And he was right. Under specific conditions, hot water freezes faster than cold water. Aristotle noticed it in 350 BC. The Royal Society of Chemistry offered a cash prize for an explanation. No entry has been accepted. The prize is unclaimed. The effect is experimentally real, replicable, unexplained. This isn't a hoax. It's a crack in classical thermodynamics. Hot water, carrying more internal energy, orders itself into ice faster than cold water. How? Multiple theories exist. Evaporation. The hot sample loses mass, so there's less water to freeze. Convection. Temperature gradients create currents that speed cooling. Dissolved gases. Hot water holds less gas, which might alter freezing. Supercool. Cold water might supercool before freezing, while hot water triggers nucleation earlier. Hydrogen bond anomalies. Perhaps quantum effects. But no single explanation reconciles all observations. For 60 years, the case has sat open. 2,000 years of noticing. Still no verdict. Two stories, both about water freezing, both riddled with quantum weirdness and unexplained behavior. Road solved. We thought we understood it for a century and a half. Then nuclear quantum effects appeared. The Mpemba effect, observed since antiquity, yet every proposed mechanism fails to close the case. What does this tell us? Water's phase transitions are not fully captured by classical physics. The most studied molecule on Earth keeps refusing to give up its secrets. Every winter we scatter white crystals on icy roads. It works. It saves lives. But at the atomic scale, it demands a quantum description. And the Mpemba effect sits there, a second unsolved mystery inside the same substance, the salt crystal. That's our exhibit. It first appeared on a dark highway, ancient and modern. Now look at it again. Dissolving, disrupting, but not the way you learned in school. The evidence says ions reach across hydrogen bonds. Nuclei tunnel. Classical simulations fail. The crystal is a mask for a quantum choreography we're still decoding. And the hot water that freezes first? That's the same molecule, equally stubborn. The Royal Society of Chemistry's prize remains unclaimed. The file is open. Here is what we know. Salt depresses the freezing point by disrupting ice lattice formation. Here is what we now add. Nuclear quantum effects are mandatory for a correct simulation. Here is what we don't know. Exactly why hot water sometimes freezes faster, or whether the quantum effects in salt water extend to the Mpemba mystery. The common thread is water's refusal to give a complete answer. The case is not closed. The salt still works, the mystery remains. For 2,000 years we've used it. For 140 we thought we understood it. Now we know better. The answer is still being written. Next winter, when you see a salt truck spraying crystals across a snowy highway, remember that's not just chemistry, it's a quantum operation. And water, the most familiar substance, is still in the interrogation room. Still holding back. The question mark hovers. The prize waits.